আচ্ছা, দাঁড়ান আমি খুঁজে নিই একবার। লাইভ। অন করে দিই। না, এটা তো অন থাকে না। Community থাকে। ঠিক আছে। তুমি এবার শিফট করে দিতে পারো সিনটা তোমার ব্যাগের জায়গাতে, বা অসুবিধা না হলে। ঠিক আছে। Welcome to the afternoon session of day 3 of the GAN course on zeros of L functions. So yesterday we ended the tutorial session with the problem of showing the sum of the reciprocals of the primes diverge. Okay, P prime is diverges. Okay, and you had given some idea the students. I mean, this was an exercise. Okay, so and then we, I mean, we said that it works, but there was some gap which needs to be filled. So could you please recall what is the idea for, yeah, take zeta s, yes, and take, okay, write down the Euler product, yes, right, all right. So then take the logarithm of zeta s, and that gives you minus sum over p log of 1 minus 1 by p power s, right? And that is, yes, then we wanted to expand this, right? So that implies log of zeta s is equal to summation over uh, p, and this series 1 by p power s plus 1 by 2 p power s up s 2s, and sorry 2s plus 1 by 3 p power 3s plus dot dot dot. That is, you expand the log series, okay, right? And now you said that you want to separate the two things, and you can do that because of the absolute convergence. You are still in the part that real part of s is greater than 1, right? So there you are allowed to do this, that is sum over p 1 by p power s plus the sum over the rest of the things, okay? That is 1 by 2 p 2s plus, wait a minute, I will clear up the right hand side, 1 by 3 p power 3s plus 1 by 4 p power 4s, etc. Okay, so now proceed from here. Yes, Yeah, you have to show that this remains bounded. Yes. And how should you proceed? Absolute value of this part. Okay. So summation p, and you want to take the everything here, right? 2p 2s plus 1 by 3p 3s plus dot dot dot. Yes. And then the inequality. But why are you okay? Yeah, because s you are taking as a complex. All right. So then this is less than or equal to summation p 1 by 2p 2s plus 1 by 3. Okay, this can go in 3p 3s plus dot dot dot. Yes. And then of course yes. Okay. So that is equal to summation over p 1 by 2 p power 2 real part of s plus 1 by 3 p 3 times real part of s plus dot dot dot. Yes. 1 by 2p square 1 by 3p square 3p cube. Yes, because real part of s was supposed to be greater than 1. Sure. Yes. Wait a minute. Real part of s is supposed to be greater than 1, right? And now we were in the denominator. So what happens there? Let's check. So real part of s is greater than 1, and then that means p power real part of s is greater than p, right? And so 1 by p is less than uh, okay, now we are taking squares, right? So p squares will be squared, and then this is less 1 by p squared is less than p power 2 real part of s. So it is not binding it from up, but it is bound. I mean, so p squared is smaller than this, right? You want to bound it from what? Yeah, yeah, sure, sure, sure. Of course, yes. Okay, thank you. Yes, of course. Right. Yeah, and then you put okay summation 1 by p summation p, and then okay, right, 1 by n. So this is strictly less than 1 by 1 by 2 p square plus 1 by 3 p cube plus etc. 1 by p square plus 1 by p cube. Yes, of course, yes. Okay, and this is less than summation p 1 by p square plus 1 by p cube plus dot dot dot. Okay, and then that is giving you summation p 1 by p square, and inside you are having 1 by 1 minus 1 by p. So this is summation over p 1 by p times p minus 1. So your is finite because it's a quadratic term. Okay. Sure. So that shows that the part which is except this summation 1 by p power s, the rest of the term remains bounded, right? Right. The left hand side um, shoots up. I mean, it goes to infinity. So the right hand side this should also go to. Very nice. There is another very nice proof of this, an elementary proof by Erdash. Have you ever seen that? You, that is, it doesn't use the zeta function, but it just uses elementary combinatorics. Not I mean, so well, it's counting a set from two ways, by two ways. So one is, so suppose that proof is very short, and we can also see this once. So this was a divergence of primes, summation 1 by p. P diverges, and this is a proof by Erdash. And it's a very nice argument. That is, so if otherwise, I assume that it converges. Okay, so that means if you denote the primes by p1, p2, etc., then, and if you write this sum as summation 1 by pi, I running from 1 to infinity, then there exists some k after which this, I mean, so this could be written as summation I running from 1 to k minus 1, 1 by pi, plus summation j running from k to infinity, 1 by pj, whereas this part is less than half because it converges, right? And then he chose some x, this x to be, I mean, precisely told. So we're taking some positive x. Okay, this x has to be chosen later. The right order of x should be chosen later so that we get a contradiction. But for the moment, suppose x is somewhere on the positive real. Okay? And now consider the numbers less than equal to x, which are not divisible by any of these primes, which are occurring in this part. Okay? So let the set, call this set to be some mx, to be the set of all primes, all numbers less than or equal to x, such that none of them are divisible by pk, pk plus 1, or any higher primes. Okay? In other words, all these numbers in mx are not only less than equal to x, all the factors that they can have are coming from this p1 to pk minus 1. Okay? So now if you would like to write these numbers of, I mean, the elements of mx as product of a square and a square free part, so if you write let n in mx, and then n is equal to some m squared times l, where this is a square, the square free part, and this is a square. Okay, so and m and l are coprime. Okay. No, m and l need not be coprime, because suppose it is divisible by some p cube. Okay, it need not be coprime. Okay. So, and we know that the numbers in mx are, well, they are less than x, right? So what are how many possibilities are there for m square? At most 2x possibilities, right? So at most root x possibilities for M, and how many possibilities for L? Well, the divisors of L is a square free part, right? So L is square free. L is square free, and all the divisors of L is coming from the first k minus 1 primes. We said that the higher primes pk plus 1, these are not, I mean, these numbers in mx are not divisible by the higher primes. Okay? So the square free part can come just from products of the first few primes, okay, first k minus 1 primes. So there are at most 2 power k minus 1 possibilities. Okay, we choose none of them, or we choose all of them, or we can choose any subset of them. So at most, okay, exactly 2 power k minus 1 possibilities for L. Then how many possibilities are there for N? The product of these two, right? 2k minus 1 times root x at most. Okay. So that implies the cardinality of mx is bounded by 2 power k minus 1 times root x. Okay. If the voice is breaking, just ask them to switch to YouTube. So these times we have tested and it will be better. 2k minus 1 root x. Okay, this is an upper bound for mx. Now, not one more thing. Okay, now let's check what is the number. I mean, what is the cardinality of the elements in this set which are not in mx. So now we are estimating the cardinality of x minus mx. Okay. Uh, well, x minus the cardinality of x. Okay. And that means now we are considering counting the numbers which are divisible by at least one of the higher primes, right? So for example, take pk. How many multiples of pk could be in this interval? At most x by pk. How many multiples of this could be in this interval? At most x by pk plus 1. Okay. So number of multiples of pj which are less than x is at most x by pj, right? So that means this set has the cardinality, I mean, x minus this is less than or equal to summation x by pj, right? Where j is running from k to infinity. And what is this? This is, well, 1 by pj, summation j running from k to infinity was bounded by half. So this is less than x by 2, right? Okay. All right. So x minus this is less than x by 2. Now what happens if you take it to the okay? What have we obtained here? That x minus is less than x by 2, and that means the cardinality of mx is larger than x by 2, right? But we know that this is less than 2 power k minus 1 root x, and that is giving us a contradiction for x large. Also, is less than or equal to 2 power k minus 1 root x. So that implies x by 2 is less than 2 power k minus 1 root x. That is, root x is less than 2 power k. Okay. But if the set of the, I mean, some of the primes diverge, then this k, we can fix some k, right? So as that summation 1 by pj for j larger than or equal to k is bounded above by half, and that k is fixed. Now once that k is fixed, this x cannot be chosen to be larger than 2 power k, but we can choose x arbitrarily large because this argument is general, right? So that's the contradiction. So the next thing actually connects with this problem of divergence of the reciprocals of the primes in this manner. So this is the next exercise. Let Qn be the least prime divisor of n factorial plus 1. Show that summation 1 by Qn for n running from 1 to infinity diverges. Okay. So how to show that? Take a few minutes. It's a trick question, but it's nice. Yes. Yeah. Yeah. Tell me. লাইভ কতক্ষণ চলছে? আচ্ছা, ঠিক আছে। So yeah, tell me what is the idea? Yes, that's a question, right? It is, you fix a prime, n is prime, right? You fix it. Yes. Yes, is that possible? So you are saying that for every prime we can find such an n. So can you give an example? You are on the right track. P minus 1 factorial. So you are saying that here n can be p minus 1 factorial, and we are considering p minus 1 factorial plus 1, and that should be divisible by p, and P should be its least prime divisor. Why? Have you seen Wilson's theorem? It is, yeah, okay. And it is, of course, the least prime divisor because everything before it is in this, right? So what happens if now I change this sign? So that's of course the right idea, right? And now suppose do this, and then how do you proceed? This is also easy. Okay, how? P minus 1? No, this time P minus 1 won't work because P minus 1 factorial minus 1, that Wilson's theorem says that P minus 1 factorial plus 1 is divisible by P. Yes, yes, of course, yes. Yes, multiplicative? Yes. But we just saw that the earlier one was solved by Wilson's theorem rather simply, right? So this, I mean, you can actually see that the only thing between 1 to 1 to between 1 to p, which in the multiplicative group, which is congruent to minus 1 modulo p, is p minus 1. Remove that. So you have p minus 1 factorial congruent to, I mean, when this was plus in the previous problem, you have p minus 1 factorial congruent to minus 1 modulo p, right? Now remove that minus 1 modulo p from both sides. You get p plus 2 factorial is congruent to 1 modulo p, right? So use that here, and you are getting all the sequence of all the primes here, which diverges. We just proved it. Okay. So proof is the first one for n factorial plus 1, just Wilson's theorem, n factorial minus 1. Note that p minus 2 factorial minus 1, this is divisible by p. Okay. And you are done. And that follows from Wilson's theorem as well. So it's a corollary of Wilson's theorem. Okay. All right, now we do something essential for the, I mean, this we should do before we proceed with the proof of the prime number theorem, because you must know what is Abel summation formula. I hope some of you know, but if you don't, please take this as exercise and do this in a moment. So let an be a sequence of complex numbers and let f be a function, okay, be a continuously differentiable function on 1 to x. Okay. Show that summation a n if n less than equal to x, this is equal to ax if x minus, oh, okay, wait a minute. integral from 1 to x at f dash t dt. So please proceed. Please take a while. Do this. Ah, right. Of course, yes. Thank you. Where ax is the sum over this n less than equal to x. Yes. Thank you. Oh, did we send it? We did, right? The link. Okay. Could we just check? Okay. And did he reply that it is updated? No, we just sent before this class began, right? Okay. Thanks. Sure. Yes. But this, of course, yes. Yeah. Well, maybe here we then with axfx we have the other thing minus ayfy, the lower limit. We have to check whether we can get rid of the lower limit or not. But this will suffice for what we are going to see next. Indeed, yeah. So have you started or are you already done, Ria? Okay. A hint is that you can start with writing an as an minus a minus 1. So start with that, writing it there. Yes. Yes, with the Riemann still yeah, Riemann still it's just one line. Yeah. 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 So if you start with this, then you have an fn. This is equal to summation n less than equal to x an minus a n minus 1 fn, right? And this one is equal to, if you separate these things out, this is an fn minus summation. Well, this is a n minus 1 fn, but if you take the sum, okay, at first let's write it down as it is, and then we change the time variables inside. So this one, we would also like to write it as an instead of n minus 1, and therefore we will write that fn as fn plus 1. Okay. So that means if we take out the first term, that is ax fx from here, then both of the sums are over the n's which are less than or equal to x minus 1. Okay. So this becomes plus summation over n less than or equal to x minus 1 a n times uh, okay, so this is if okay, so if we take the minus sign outside, then it will be fn plus 1 minus fn, or the integral. Okay, let's at first go step by step. So this is fn minus fn plus 1, which is equal to ax fx plus uh, summation n less than equal to x minus 1 a n integral of f dash t dt from n to n plus 1, and here it is minus because we have changed the, I mean the limits are n and n plus 1, and we assume that f is continuously differentiable, so we can do this. Okay. Note one thing, that this is a step function. Okay, so from n to n plus 1 its value remains fixed, right? So we can take 80 inside. Now if x would have been an integer, this already settles the claim, because well, this if you club up all these intervals, then it goes up to, this was up to n less than or equal to x minus 1, and this is going to going up to n plus 1. So this is running up to x. So if x is an integer, then the then summation n less than or equal to x minus 1 integral from n to n plus 1 at f dash t dt, this is just equal to the integral from 1 to x at f dash t dt. Okay. What happens if x is not an integer? Then we note that we have the same thing. I mean, we have whatever we have done till now, we have established this for the floor of x, right? And note one thing, that ax times fx minus f box x, this one is the integral from box x to x at f dash t dt, right? If x is not an integer, because again this is a step function, so the value of at won't change over this, right? And then you have that this is equal to this, so ax fx minus ax times f of x, well, ax times f of box x or floor x is the same as x a of floor x times f of floor x, right? So what we have here, So till now you have that summation an if n less than equal to floor x, say this is equal to a floor x if floor x minus the integral from 1 to floor x at f dash t dt, right? And now using that, what do you get? So this one, so this is the first thing that we have proved till now. Okay. And the second thing is that ax fx minus, well, as we mentioned, ax time x is just a of box x, okay, of floor x. So this is a floor x, f of floor x. This is equal to the integral from floor x to x at f dash t dt, right? So if we call it 2, okay. Now if we add this and this, what happens? Okay, if we add this and this, the first, okay, I see. This needs to be cancelled. Now this we take on the left hand side, that means this, so, or right hand side. So this means 0 is equal to, okay, wipe this out. And here you have ax fx minus a box x if box x minus integral from box x to x at f dash t dt, right? Call this as equation 2. It is just equal to 0. Add this with this one. The left hand side is just n less than equal to box x. Okay, this was the integers, so this is the same as summation n less than equal to x an fn, right? Because we are summing of the integers, and here you see that this part cancels with this one, and this one just gets added with this one to give the integral from 1 to x. Okay. So now we are going to use this over, so we should not wipe this out entirely, or have we already done it? This was, okay, okay, we have written it anyway. So we can first clear this part, and we're going to apply this on Dirichlet series. Okay, so suppose now summation an by n power s n running from 1 to infinity be a Dirichlet series such that ax, that is summation an n less than equal to x, this is big O of x delta for some delta, some power delta for some, okay. Then actually we don't need even delta, I mean some delta is fine, some delta dl, okay. Then we have that n running from 1 to infinity an by n power s, this regular series is represented by this integral s from 1 to infinity a x by x to the power s. Okay, we'll okay, this is wait a minute, s plus 1, sorry, dx, okay, for all s larger than delta. And in particular, note that since ax is big O of x per delta, that means this integral converges in this region. So this series converges for all s larger than delta. Okay. So please do this using the previous thing. Yeah, right. So choose your function to be fx to be 1 by x power s, and then use the Abel summation formula directly. Okay. That gives you this. Okay. So let fx be equal to 1 by x power s. Then summation an fn n less than equal to x, this is equal to what? Ax fx. Well, we can actually write what we have taken as the, I mean, what is the definition of f, right? So an by n to the power s, that is fn, right? And here ax fx, so ax by n to the power up x fx, so x to the power s, minus the derivative of this. What is the derivative of this? Minus s by 1 by, or you are taking f dash t, so let's write it down here, s integral of a t t power s plus 1, right? And the integral from 1 to x. What? The minus, oh yeah, 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 sure, sure, thanks, because we have a plus sign here as well. I mean, that was the claim. So if the claim is true, what do you have to show? Yes, right. And this term goes to 0. Okay, so okay, yeah, so this one, yeah, tell me. X, yeah, x is, when s is greater than delta, then this is big O of x power delta. So when s is greater than delta, that means that if you take x going to infinity, when x is very large, this term is as small as you wish. So in particular, if you take x go to infinity, on the left hand side you get this series, on the right hand side you are just getting this integral from 1 to infinity, okay? Because this term goes to 0, goes to 0 as x goes to infinity. And of course this integral converges because at is of size t power delta, right? And s is, so this integral converges for all s greater than delta. So indeed you have obtained that this is given by this if the summative function of an is big, I mean, if is of this order. And can you conclude from here that this converges on some half plane, or do we need more strong condition, stronger condition on this? Yesterday we saw about convergence of the Dirichlet series, right? That what is the convergence condition? Was it if it converges on some point? I mean, here we are taking s greater than delta. So we would like to replace this s with real part of s greater than delta. Are we having sufficient condition for that? Or do we need something else? It's sufficient. Could you just check your notes from yesterday whether it is sufficient? A small thing is missing. Absolutely convergent. You need absolute convergence of that. So instead of this, you require if ax is summation, well, you define some, well, define ax to be just sum of the absolute values to be big of x delta. Okay. If, well, you don't even need to define it. If you just have this condition that sum of absolute values of an up to x is big of x delta, you can tell immediately using that, using what we have done there, that this series converges absolutely for all s larger than delta. But that means now you can, I mean, the thing that we saw yesterday, we were taking the absolute values of this, right? And that's why I mean, that was the reason we could actually go to the just a just a real line. I mean, we were just considering the real part of s greater than delta, because the imaginary part, when you are taking the absolute value here, it is yielding just n power, that imaginary part is just one absolute value of that, right? So that's why you need this condition instead of just this condition. Okay. So if that is satisfied, then summation an by n power s, n running from 1 to infinity, converges absolutely for all s with real part of s strictly greater than delta, right? Now, does it mean that real part of s equal to delta is the axis of convergence? The question is whether real part of s equal to delta is the axis of convergence of this Dirichlet series. In that case, if this is big of x power delta, so this is a question. You recall what was abscissa of convergence? What was it? Please tell me. Right. So on the right hand side of so it is a right plane in which um, the Dirichlet series converges, and it is the boundary of the right half plane. Now, whatever information you have from here, does it imply that this line is a boundary of that? It's not. It just says that this line is in that region. I mean, somewhere in that. Right. Exactly. So big O of x power delta doesn't hinder it from being of some order less than this. So if it is big O of x delta, it could also be big O of x power some smaller power, some I mean some delta dash, which is smaller than delta. Okay. Let's write. I mean, let's be clear about this. What I just meant here. It's a basic question, but we must get the basics clear. So the thing is that if something, if fx, for example, say is of big O of x power say 4, what does it mean? That limit fx by x power 4 x goes to infinity. We are taking, I mean, assuming that big O of x power 4 as x goes to infinity. So this is less than equal to some constant. This is meant by that. Okay, but I mean, this doesn't stop it from being of some order less. For example, this. So let's say let fx be equal to ax square plus b for some a and b. Note that if you take this limit, then the limit is 0, right? It's some constant. Okay. Well, it's 0, and we assume that when we are writing that c is some positive constant, but nevertheless, it is less than any positive constant if it is of this form. So that means if a function is of some given order, that doesn't mean that that order is the minimum order for this. Big O of means that it is this one is bounded just. So that means if you are given this condition, this need not be the abscissa of convergence. The abscissa of convergence could be somewhere on the left of this. Okay? All you can say is that the abscissa of convergence is not on the right of it, on the left of this. Okay. So now the last problem for today. So let, okay, you know what is zeta function, right? So the exercise is just to show that zeta s is 1 by s minus 1 plus b of 1. Okay, as, okay, and also figure out in which range. Okay, as is goes to, okay, or for s larger than, that's fine. And this should be a direct application of whatever we have done till now. Okay. Acha. Okay. Yes. Right. Yeah. Yes. 1 by. No. So you have to. You are actually using the Abel summation formula again, right? Or if you have, I mean, we have seen the general case, the general case with the Dirichlet series. This one. Okay. We just saw that this has an integral representation. Okay. You know where this converges, right? That on, I mean, for real part of s greater than 1. So you can take delta to be equal to 1. Okay. If you take a n to be equal to 1 for all n, that means ax is the sum over n less than equal to x. What is that? Very good. It's a box of x. Okay. Yes. And then, so that means summation a n by n to the power s, n running from 1 to infinity. This is equal to, well, s integral from 1 to infinity box of x by x power 1 plus s, right? Or s plus 1 dx for all s. Um, well, for the moment, let's take s to be positive. I mean, some real number that for all s greater than 1. Actually, this this integral formula is more general, but nevertheless, since we did everything for the reals and then we went to complex numbers after actually this also satisfies that condition. You see, you take the absolute value of a n, it's just 1. So this is of the order x power, I mean, it's box x, so it is just x power 1. So in particular, from the integral representation, you can also conclude immediately that the series, the zeta function that we just, I mean, that we are taking 1 by n power s, right? And that converges for s greater than, a real part of s greater than 1. But we have already seen this. So now we have to go from here to there. How do we? Okay, this one we break it into parts, x minus fractional part of x, right? And here, since we have taken a n equal to 1, we just write here 1. So this one becomes then equal to s times 1 to infinity x minus the fractional part of x by x power s plus 1 dx. Okay, and that is s integral from 1 to infinity dx by x power s minus the integral from 1 to infinity again x by x power s plus 1 dx, right? Now what is the first integral? Yes, right. So there comes, okay, it is s by s minus 1, and here x power s minus 1 as well, and the negative of this, right? So this will return infinity and 1, right? But I haven't understood. X to the power, wait a minute, the integral was, after integration you are getting x to the power minus s. Right. Sure, 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 sure. But it was x to the power minus s, right? So it is minus s plus 1 should be, and then it is coming below, right? So it is just s minus 1. And then s minus 1 is there. Right. Yeah, sure. Of course. Yeah, yeah. And if you put the, well, but if you put the value, then why it should be plus? Because I haven't evaluated this yet. Okay. This is, wait a minute. Let's do this. Okay. So x to the power, we are having x power minus s here, right? And we are integrating it. Yeah. So we are integrating it from 1 to infinity dx. This is the thing, right? And then what we are having, so this should be coming from x power minus s plus 1, and then at the bottom, yes, minus s plus 1. Okay, so that is x power, it is equal to minus s minus 1 times x power s minus 1, right? And that's what I have written there. Okay, so minus s. Okay, now note one thing, that this remains bounded by 1. Okay, and so for real part of s greater than 1, this integral converges. Okay, so okay, let's let's keep it as it is for a while we'll deal with the first one, and then we'll come here. So 1 to infinity x to the power s plus 1 dx, and this one after you evaluate at infinity is just 0, at 1 it is s by s minus 1. Well, s by s minus 1 could be written as 1 plus s minus 1 by s minus 1. So this 1 by s minus 1 comes out, right? And you have plus 1. Okay, and then minus s integral from 1 to infinity box x by x power s plus 1 dx is there, right? So now this one, okay, well, we have just did something there. Okay, instead of having s here, think of having s plus 1 there, because this part is bounded by 1. This is a fractional part of x, right? So that integral, I mean, forget about this s on the right, or you can actually not forget about this, because that will get cancelled with this s minus 1. I mean, what, yeah. So here we are having now this thing, right? And this is just giving you then minus s minus s. So if you multiply it from minus by minuses from the outside, you get this minuses cancelled, right? Okay, and you have this x power minus s from 1 to infinity, which is just giving you 1, right? But that's an upper bound for that, this this thing, because we have taken this to be less than, I mean, this is less than equal to 1, right? So this one, the entire thing can have value at most 1. Okay, so 1 minus this is some positive thing. Okay, so that just means that this one is bounded by 1, and we can of course write this as big O of 1, right? So this entire thing is well, we have already received our claim, that is zeta s is equal to 1 by s minus 1 plus the rest of the thing. This one is just big O of 1. That's it. So that's all for today. We continue with the proof of prime number theorem tomorrow morning. Thank you.